All right, good morning, everyone. Thanks for joining on the early sessions. My name is Tom. I work as an applied scientist at AWS. And today I'd like to talk to you about a project I worked on with the BBC. Now I realize in the abstract for our session, we've got quite a generic title and abstract. So apologies for that. This session will focus a lot more on natural language processing, and we'll look at an application using Apache MXNet and an associated package called Glueon NLP. But I hope you still take a lot out of the session from how to use these tools. So I'm here today with Ben and Neil, who are just over on the side of the screen there. And they're from the BBC. So Ben is a lead data scientist, and he's going to introduce and give some context around machine learning at the BBC, and then specifically talk about some of the challenges that the BBC faces regarding that. Then he's going to hand over to Neil, who's going to give us a deep dive on the BBC programs team, and specifically give us details on the segment enrichment experiment that was done for text segmentation. And then after that, I'm going to give you a run through of the tools that we use to improve upon the baseline model, which include Amazon SageMaker, Apache MXNet, and Glueon NLP. And because this is text segmentation, I want to give you some background as to some of the theory and the science behind it, but then really give you some takeaways, how you can use Glueon NLP to solve natural language processing tasks. So we'll look at the implementation details for that. So with that, I'm going to hand over to Ben.
Thanks very much, Neil. That was Tom. Great, how's everybody doing this morning? So let's talk just a little bit about machine learning at the BBC. So I just want to sort of walk through a bunch of the projects that we have in our organization, and there's quite a few of them, so I'm going to organize them based on a couple of different things. One of them is whether or not the tools are principally for an external audience or for internal use. So we have a lot of people that produce content, people that make editorial and commission decisions, and some of our machine learning is for internal users. And then what data is used in the machine learning. And we're going to think about this as kind of being a spectrum from content and analysis of that content down to audience profiling. So that's the kind of stuff that you would think of for maybe building a recommender or understanding behavioral trends among media consumers. So to start with, BBC News has a article recommender for its online service. So if you go to BBC News Online, you will see an interstitial about halfway through the article that directs you to some similar content. This particular system is entirely using content analysis, so it looks at the actual text in the article, finds similar text, and we'll speak a little more about that a little later. In contrast, the iPlayer's recommender system, because it sits in a slightly different domain, so this is our on-demand video player, principally for a UK audience. It uses a much more sort of traditional recommender approach, a bit of audience data. There's also a fair bit of content involved as well, so metadata awareness, a lot of editorial rules, things like this. But it's still a sort of closer frame to the sort of most generic idea of a recommender system. Then we have a kind of interesting newer project of ours from BBC Children's, our brand that's focused on entertainment for kids. This project is called Own It, and it's a sort of introduction to using a cell phone. And so it's a custom keyboard that sits on an Android or an iOS device, and it does the sort of standard things you would expect a custom keyboard to do, autocomplete, that sort of thing, but it also effectively pays attention to what's being typed and what the context is that's being typed, and tries to gently assist and reinforce good behavior with a cell phone. So trying to sort of push people away from bullying, but also to keep people safe, not share personal details with strangers, things like that. And then we have a audience segmentation tool. So in some ways, this kind of a tool feels a lot like traditional marketing and analytics use case, except that it cares a bit more about behavior and less about demographics. So we try to group our audiences based on how they interact with our tools and our brands. So are you just a news consumer? Do you watch a lot of broadcast television? Are you a radio consumer? Do you visit us often but not very long times occasionally? or is this your first time you've ever seen you, that kind of thing. And that's a good guidance for understanding the kind of people that consume what sort of content so that we can better optimize what we're making. And then finally, we've got a sort of suite of internal tools that we use for content analysis. The first of these is called Mango. Mango is a entity recognizer. And so it's going to go through a block of text and find pronouns, events, places, things like this. And then it maps them to a database of things that we have, which is cleverly called BBC Things. And it has a sort of semantic web norm, so everything gets URLs and that kind of stuff. It's quite useful to work with. On top of Mango, we have a tool called Starfruit. And Starfruit comes from the fact that frequently for us, what we actually want when we're doing this entity recognition is not all of the things that are mentioned in a block of text, but an understanding of what the text is specifically about. And Starfruit effectively builds a classifier on top of the entity recognizer. So you can say, for this entity, is this article about that? And it's trained on editorially generated tagging information that we have been using to organize our content for quite a long time. And then the last thing I'll mention, which is sort of both internal and external depending on how you face it, is the linear segmentation tool that Neil's going to speak about at some depth later on. So just to kind of give you an idea of the challenges we face when we're thinking about machine learning projects at the BBC, most of what we tend to build is in-house to some extent, and the things that aren't in-house are wrapped in so much sort of customization that they very nearly might as well have been. And one of the reasons why we have to do this is because a lot of the domains we work in don't sort of fulfill standard off-the-shelf briefs for various machine learning packages. For a lot of the stuff we're trying to build recommenders for instance, we have very sparse content, both in terms of understanding item preference and also understanding user behavior. So modern news users tend to be very brittle. They come through aggregators, they read one thing, they wander off, and the life cycle of a news article is very short. So by the time you understand it, it's not a thing you want to recommend anymore because it's not news. We have similar things so for instance, for a lot of our video, we have regulatory requirements that mean that we can't recommend and promote older things in some contexts, a bunch of things like this. Additionally, we're a public service organization, we're principally taxpayer funded, and so that means that we operate with a sort of broader remit than a commercial organization that's just trying to make more money effectively. So frequently our machine learning will have multiple optimizations. I think that's interesting as a data scientist. It also makes the problem a bit harder. We like to talk about this as needing to inform, educate, and entertain in all the things we do. So you can think about that as having kind of proxy metrics for each of those things. And we're also interested in a sort of broad pickup of our content. So are you just reading celebrity news? Can we drag you over to some harder stuff? Are you just engaging with entertainment content? Can we do a bit better than that? We also have regulatory requirements. So we're in the UK, so we have to meet the GDPR, which is a data privacy regulation from the EU. And that kind of restricts what we can do. We also have other ethical constraints around privacy for some of our other services. And then lastly, there's a big need for us to have editorial control and editorial oversight over our tools. This is better from some commodity tools than it was a while ago, but it's still something that frequently takes a bit more effort to get out of a lot of machine learning to make sure that they're reasonably transparent and inspectable. And the last thing is that for a lot of our services, news in particular, we operate in many languages, and some of those languages are not very commonly supported in pre-trained models, for instance. So in particular, if we just pick at news for a little while. So we operate World Service Online, it's called, in 41 languages, I think is the current count. And mostly in non-European or North American markets. And it's a wide range of languages. Some of them are very widely spoken and supported by a lot of NLP tools. Some of them are not. And if we flip over to just sort of see the recommender in action that we've got built here. So here's BBC Mundo, which is our Spanish language service. It mostly serves a Latin American market. This is an article about being a bit time stressed. And so if we scroll down halfway through the article, you'll see a little break. It suggests more articles that are similar. And then you can see what you have here is some kind of self-help tone things, a health article, that kind of thing. And this is all content-based and doesn't really care about the user. So another one of our tools to pick out a little more, this is the tool from BBC Children's, Own It. So you can see here some stills from the custom keyboard. There's a very sort of playful emoji feedback you get when you're typing things in that kind of encourages better behavior. So when you're doing something sensible, you get a nice green smiley face. When you're doing something maybe a bit unexciting that the model doesn't think is good behavior, it may gently discourage you with some feedback. It also has a few features that are not machine learning but make the product exciting and usable. There's a gamification thing around badges and a diarying function, so you can sort of tell it how you're feeling that day, how your life has been, that sort of thing. And I would encourage you, if you have children in sort of preteen range, to give it a download and check it out. It's quite an interesting product. So I'll just spend a little bit of time last getting into a bit more detail about how Mango and Starfruit work. So as I said earlier, Mango is a named entity recognizer, and Starfruit is a topic modeler, or excuse me, a topic identifier that sits on top of it. So if we take an article from BBC News from about a month ago, this is a Brexit article concerning a particular sort of bit of minutia that happened back in October, where the Prime Minister met with members of his supporting party, the DUP from Northern Ireland. And if we run that through the named entity recognizer, we get in total about 24 entities extracted out, which is fine. The problem is the sort of order, if we care about understanding what the article's about. So these are definitely things that were mentioned. The DUP is the Northern Irish Party, the Conservatives, the other party. Michel Barnier is the European Commissioner, so he is involved in Brexit negotiations, but the article is not really about him in any way. So if what you actually care about is not a list of entities, but rather the topics, then you can run things through Starfruit. So we take the same thing and put it through Starfruit, and that'll get you the same list of entities. So if this was the full 24, they would be the same, but the order is now changed. And specifically, the scores now reflect how much sort of aboutness we have, rather than how reliable the entity extraction was. So now what's happened is Brexit, the primary topic, has popped right up to the top, and then it's followed by politics, our broader follow-on topic from Brexit, and then Boris Johnson, the Prime Minister, who is the core protagonist of this particular article. And all of that backs onto BBC Things. So BBC Things is a public resource we have that's our tagging ontology. You can go to things.bbc.co.uk and have a look at some point. So the one thing I want to point out here is that because it's a semantic graph, you can leverage that when you're doing search. So if I type in Boris J into the search bar, what comes back is the literal string matches, Boris Johnson the politician, but also things that are semantically close. In particular, that last link, Carrie Simons, is Boris Johnson's partner. And so that's not doing a string lookup of the description, it's actually walking the sort of close things in the graph. And that's quite powerful for doing sort of item organization and things like this. Yeah, so I'm just going to hand over now to Neil, who's going to tell you a bit more about the BBC Programs segmenter.
Okay, thanks, Ben. So the BBC has over 5.5 million programs in its back catalogue. Every day we release new content on hundreds of over 100 radio stations, dozens of TV channels, online, on-demand video and podcasts. And we want to connect individual members of the audience with this content. So just to illustrate the problem with this, we'll look at a few programs. So Fleabag is one of my personal favourite programs at the minute. Once a user's watched Fleabag, should we recommend Mrs. Brown's Boys, which I appreciate some of you won't have heard of, or Killing Eve, which is maybe a little more famous. So when we look at the metadata that we have, you might think they're both sitcoms, so Mrs. Brown's Boys would be a better recommendation. But for me, somebody who enjoyed Fleabag, I've watched 2 minutes of Mrs. Brown's Boys before I turned it off. And so what we need is some better, richer metadata that captures the differences and similarities between these programs. So this is what that might look like. And this highlights how similar, or the ways that Fleabag and Killing Eve are similar. They've both got sophisticated black humour, narratively driven, following a story over a number of seasons, a similar audience and strong female lead, whereas Mrs. Brown's Boys, you can now see that it's more suitable for an older audience. It's still a very popular programme at the BBC, but just not with the same audience as Fleabag. So to generate this better metadata, we've developed a content enrichment chassis. So on the left-hand side, a client can upload content, so that could be audio from a radio program, text content, or a video file, along with a plan, which is just a simple JSON document that gives instructions on which engines we want to analyze the content with. So the chassis will take care of batching, so you can put batches of tens of thousands of documents through, as well as queuing and notification of success or failure back to the client. The engines, these are some illustrative examples. So Amazon Transcribe and BBC Caldi are both speech-to-text engines. The two segmentation engines, Tom's going to go through in more detail as part of his talk. And Amazon Comprehend and BBC Starfruit are both text analysis engines. I draw out the topics and the dimensions of famous people, places, and events. We can add any engine to the right-hand side. So, for instance, if we wanted to pick out which celebrities appeared in a TV program, we could add a facial recognition engine to the right-hand side. One of the key benefits of the chassis to the BBC is the ease of integration. So, within 20 minutes, a client can create an IAM role and an SNS topic, and then they can start posting and receiving notifications on the content that they want analysed. And for the engine authors, which are typically research and development at the BBC, they can get their engines and they can integrate that in an hour or less into the chassis. So that allows them to release the work that they've been doing much more quickly than they've been able to in the past. So this followed on from a segment enrichment experiment proof of concept that we did, which is really just a pared down version of what the content enrichment chassis will be able to do. So we took an audio file from a radio program. We passed it through speech-to-text, Amazon Transcribe. We segmented it using a simple text tiling algorithm, which is a very simple way of splitting the document up into smaller chunks. Tom will go through that in more detail. We summarised those segments using Amazon Comprehend and BBC Starfruit, and then we put the results into an Elasticsearch service. So why do we want to segment the content? So it allows for factual programs and for magazine format programs where 4 topics are talked about in a half-hour or hour course of the program. It allows viewers and listeners to find the exact part of the program that they're interested in. Once they've found that one segment they're interested in, they can seek either side while they're playing back the program, see what other segments are discussed in the program. We can also present to them related segments that might also be of interest to them in different programs. Clearer topic separation and model transparency as well, to allow us to validate that the results that we get from the other engines are more easily validatable on smaller segments rather than bigger programs. So historically, segments are annotated by the editing team using an editing suite. So we can see here we've got a program called You and Yours, which is a consumer affairs program. And the editor's gone in, and the first segment is about mortgages. The second segment is about food safety and best before labels. And the third segment is labelled as starting at 11 minutes 46, and it's about banking regulations. So this means that we've got a data set that we can use to train a segmentation model. This is something that we want to do because we want to get away from the time-consuming process of editors manually creating segments, which isn't something that they like to spend time doing. So We took 3 radio programs which had good segmentation data, manually created by the editors. So You and Yours, which is a consumer affairs program we were just looking at. Front Row, which is a magazine about arts, so it covers cinema releases, book releases, musicals, etc. And Woman's Hour, which is one of the longest running programs on the BBC. First broadcast in 1946, which is a magazine program aimed at a female audience. We also added in 12 TV programs, but also magazine format, but we don't have manually curated segmentation data for that, so we can't use that to inform a segmentation model. So this is the demo for the segment enrichment experiment. So the user has clicked on Brexit, and he's been brought directly to the part of the program where the host is talking about Brexit. This is Victoria Derbyshire program, which is a daily politics program on the BBC at 1 o'clock. So the user's going to click fitness now, and you can see the segments are displayed, and you can seek through and see what the other segments are about. You notice fitness there isn't really the topic. It's part of a wider discussion about education, so fitness isn't really a good label for that segment. And you can see that we've got an awful lot of segments in each of the programs, possibly too many. And this is because we used text tiling rather than a well-trained solution to try and match what the editors were doing with the manually created segments. So, as I said, this gives us kind of arbitrary segments that are too short. That the short is a problem for us because it brings the viewer or the listener into the middle of the conversation, and the viewer might leave before the topic's fully discussed. And often, like we see there, where a topic, because it's so short, it's labelled as fitness, when really it's part of a broader segment about education. So to help us with these problems, we held a hack day, which was attended by AWS data scientists, to just discuss that further and to discuss the solution to the segmentation problem. Here's Tom. Okay. Cheers, Tom.
Thanks very much, Neil. Okay, so this was, so Neil's just shown you the baseline, and this is our starting point. And then we were going to work using some tools such as Amazon SageMaker, Apache MXNet, and Glueon NLP to improve upon this bar. So for those of you who haven't seen Amazon SageMaker before, it gives you the whole machine learning workflow, all the way from labeling data to deploying your models in an endpoint. And for the hackathon specifically, we wanted to get started really quickly. So one of the key features in the workflow that we used was the inbuilt algorithms. And there's some algorithms that are specific to natural language processing tasks. And so one of the tools we used was blazing text, which creates embeddings for text. And we'll talk a lot more about embeddings later. But after the hackathon, we realized for this text segmentation task, it's quite unique, and we need a bit more flexibility in how we develop a solution. And so for that, you can always bring your own machine learning framework of choice. For this, we were using Apache MXNet. So how many people in the audience have used a deep learning framework before, just so I can gauge the audience? Okay, so a few. This reInvent, there's been a few announcements for SageMaker. So some of these tools can help developers and data scientists. If you haven't got much machine learning experience before, then SageMaker Autopilot is a great way of creating automatically generated machine learning models for given tasks. Then if you have a bit more experience and you're a data scientist who's trained machine learning models before, we've got SageMaker Debugger, which lets you inspect how the model is learning, and SageMaker Experiments, which is a great way of tracking all of the different trials and experiments that you're running and do comparisons and find the best models. And then lastly, for deployment, there's now services such as SageMaker Model Monitor, which is going to look at the input distributions of your data to your endpoints to make sure that your model is going to get the same input as it did at training. So you can then trust those predictions more, and you don't need to retrain your model. The framework that we used for this text segmentation piece was Apache MXNet. And there's a few different reasons why we used MXNet here. So firstly, it's really scalable in the sense that when you're working with state-of-the-art models, you often train on large data sets and you need to scale across multiple GPUs on single instances and also across multiple instances. And for that, MXNet has got really good scaling performance. It's also really debuggable. So in the sense here that you can set breakpoints essentially in your neural network model, which previously hasn't been possible. And so you can inspect the parameters of your network, the gradients and those kind of things, which really helps you understand what's going on. And it's using optimized libraries under the hood, regardless of whether you're running this on a CPU or on a GPU. When you work with MXNet, typically you're not going to be working with the low-level operators. You're more often going to start with the high-level APIs. And for Python, the high-level API for MXNet is called Glueon. But even better still, if you've got a relatively common task in one of the following domains, if you've got a computer vision task, then we recommend you start with Glueon CV, because it's got a number of different utilities and pre-trained models, so you can get started really quickly. For time series analysis, we've got Glueon TS. And lastly, for natural language processing, there's Glueon NLP. So for this project, given its text segmentation, that's a natural language processing task, we opted for Glueon NLP. Some of the benefits of Glueon NLP. So first of all, it's got a really comprehensive model zoo. So there are hundreds of different pre-trained models that you can use out of the box. This covers things like different types of embeddings for word levels, and also language models, translation models, and things like that. When you're using pre-trained models, though, it's really, really, really important that you transform your data in exactly the same way that was used for pre-training those models. And this can be really tricky to do. If you make small mistakes here, that can have a big impact on the model performance overall. So included in Glueon NLP, for each of the models in the model zoo, we have the transformations that you need to apply to be the same as what was used for pre-training. So that's really important. And then lastly, we've got a lot of tutorials and examples that you can find to help you get started with using Glueon NLP. Now let's talk a little bit more in detail about the segmentation approach. At a high level, because we want this to fit into the content enrichment chassis that Neil talked about, and that takes in different forms of content. So we might have some program data that was on TV that has some visual component, audio, it could be podcast, or we could have textual information such as news articles. But to create this text segmentation model, we convert everything to a common denominator, which is text. So for audio in this case, we transcribed it to get text. So now we can create this single segmentation model. There's a few limitations here for certain types of data, clearly. So we're ignoring any structural information that we might have, like paragraph indents and things like that, or visual similarity over time. But for now, this was our starting point, and then we can expand from there. What does segmentation look like in practice? So here on the left-hand side, we've got an example document. And the idea here is to separate this into chunks, where each chunk talks about a single topic, ideally. And to create a segmentation model, that's one of the key features we're going to use. We're going to look at how the topics are changing in the long term across the whole document. But also, if you zoom in to a particular topic change, you can see there's other information that we could use. So at the end of the yellow segment, for example, we've got some thank yous. And so we've got some outro, so we can pick up on a few of these words. And then at the start of the next sentence, we've got transition words such as now, and then some introductions. So we've also got this short-term signal that we want to capture. So we need to include both of these sources of information into our model. Now we've got to think about how we formulate the problem of segmentation. So you might, on first impression, form this as a classification problem, where you want every segment to be a separate class. But then this is an open set problem. We don't know what classes we're going to have in future for different documents. So instead, we can represent this problem with a binary classification. So we're just labeling true or false, whether we get a segment change at a given point. And we can do this at different granularities of time. You could do this at the character level, or you could do it at a word level or a sentence level. And so for this project, we're working at a sentence level because this gives us sufficient granularity. But there's a slight modification here. So the text tiling algorithm uses something called a pseudo-sentence, which is a fixed number of tokens consecutively. So we're not using the same sentences. But this gets around the problem of having particularly short sentences. And so when we're working with embeddings and we're averaging across different length sentences, this actually does help for those cases as well. But we just stuck with that idea from text tiling, with a 1 indicating that the topic has changed during that pseudo-sentence, and a 0 representing that it's a continuation of the topic before. With every machine learning problem, one of the very first things you should do is establish a metric that you're going to evaluate your models on. And for text segmentation, there's a specific metric that's used in papers, and it's called PK. So PK compares what the model predicts with the ground truth label from the editors, and it takes a sliding window approach to evaluate how good the model is. So we start with a sliding window of a certain size and compare whether in the prediction there was a segment break, and then compare that to the label to see whether there's a segment break. If those two match, that counts as a success. But as you move across, we can see in this case, we've now got a failure because there's a difference between what the model predicted and the label. And you do this for every step through your document and finally aggregate. So here we had 3 mistakes out of 8 possible sliding windows. So our PK is 37.5. And we're trying to minimize this metric where possible. We want to reduce the amount of errors from our model. And the reason why I introduce this is I'm going to keep referring to this PK metric for the different models that we look at. Just want to give you some background on this baseline method that we're working with, text tiling. It's been around quite a while, and it uses something called a count vector, which has been a traditional approach used in natural language processing. It compares the count vector from some pseudo-sentences with the count vectors from the following sentences. And then we can say that this count vector is essentially trying to describe those sentences. And we've got a description from some sentences, a description from the next sentences, and we calculate a similarity score between these two. We calculate the similarity of these sliding windows as they move across the document, and we try to identify the points where the similarity score drops, where 2 pseudo-sentence blocks become dissimilar, and that's where we establish these breakpoints in our model. So that's how the prediction works with text tiling. But using count vectors is a pretty naive approach and has a lot of problems in practice. So if we looked at 4 specific sentences here, the count vectors might look something like follows. Count vectors typically have thousands, if not millions, of different features because you have a feature per word, and every word has a corresponding count of how many times that word has appeared in those sentences. So this leads to a really sparse representation. We have many, many more 0 features than non-zero features. And it makes the comparisons between 2 blocks of pseudo-sentences really hard and sometimes pretty meaningless because you have the curse of dimensionality. We've got too many features and they're very, very sparse, really hard. And we can show this visually by looking at a cosine similarity plot. So cosine similarity is a typical measure of similarity of vectors. And what we're looking at here is all the sentences in a particular document, and they're compared to one another. So it's like a cross-correlation plot across all the sentences. We have about 80 pseudo-sentences in total across the document, and the green markers indicate where the editor has labeled that the segments should be. So that's our ground truth. And the ideal pattern that we're looking for in this plot is something like follows. We want high similarity between sentences in the same segment, so that's indicated by the yellow. And then we want low similarity between sentences in a segment and all the other sentences outside the segment. So this would be the ideal pattern to look for in a model. Even with a modified version of text tiling where we add different levels of smoothing, we can start to see that there is some signal in these count vectors when you look across large block sizes. But it's really hard to distinguish exactly where these breakpoints are. And looking for these dips in similarity that I mentioned, we can establish that there's 2 breakpoints according to this model, one of which is actually correct, the other one not quite, and a lot of breakpoints have been missed. So overall, on a held out test set of 1,000 documents, we have a PK score of 28.9, and that's our baseline to beat with all these models that we're going to look at. With Glueon NLP, we've got all the basic operators that you'd expect. So these things you might be familiar with in packages like NLTK, which is a common Python library for natural language processing. So we've got tokenizers across lots of different packages, such as Spacey. And that's going to break a sentence down into words, or also called tokens. We have counters that are going to count up these tokens, and things like vocabularies. So when we're working with machine learning models, we need to convert those strings into some kind of number that needs to be passed into the model. And to do this conversion, you can construct a vocabulary. So if we broke the sentence down and we had the word British, then you can pass that to the vocabulary and get an index returned that represents that word, which is 440 in this case. And you can always work backwards as well, so you can pass that and you can pass 440 into your vocab and get the word back. Now, as a step up from these count vectors, it's been a really common approach to use something called a word embedding. And here, we're looking at similar word embeddings. So I've looked at the word embedding for BBC and looked around in this embedding space to find the most similar words. And you can see here that these embeddings pick up on semantic understanding of words. And so these are much, much more useful when trying to describe text than just saying as a count that the word exists or not. These are word embeddings, but we're working with long documents that are broken down with sentences. So we need some way of going from the word embedding to create a sentence embedding. Now, there's lots of different techniques for this, and one of the sort of standard typical techniques is to average across all of these word embeddings. There's some limitations with this approach, but this is the sort of a baseline approach you can take. You can take the maximum value across all of these word embeddings as well. You can even use these as part of neural networks to create your sentence embeddings. But for now, we take the embedding from all the words and just average up every number. And we'll count that as our pseudo sentence embedding. You'll notice that the word embeddings here are what we call dense. There's not as many features. We typically have 50 to 100 different dimensions rather than thousands and millions. And we don't have zeros, so it's not sparse. So we call this a dense representation of a word or a sentence, which means the comparison is much, much better than with count vectors. So if we look at our plot again, we see some slightly different patterns emerging based on the cosine similarity. We see a big difference between segments 2 and 3, for example. And so we've got 2 accurate segment breaks. We're still missing quite a lot here. And I'll explain why looking at the cosine similarity on raw word embeddings might not be the best approach. But with Glueon NLP, it's really easy to get these word embeddings. So we can import Glueon NLP. Typically, you do it as NLP, as an alias, and then reference the embedding subpackage. On that, you can choose your type of word embedding, and there's many different variants. We've got over 180 different types of pre-trained word embeddings that you can choose from. And we'll specify that we want the glove embedding in this case. You've got a few more options, even beyond this point. So first of all, you can choose the data that this embedding was trained on. So here we're using 6 billion tokens for training. And then the dimensionality of your embedding. So in our slide previously, we saw an embedding size of 4. That was just to illustrate what an embedding was. But typically, you'll be working in the range of 50 up to 300. And that's as many features that represent each word. Once we've got our embedding, we can use this pretty similar to a dictionary in Python. So you provide a word, and it will do the lookup of the associated embedding. So we'll do this for 3 words, BBC, television, and Vegas. And each embedding has a shape here of 50. So this is an MXNet array, like a NumPy array, but can work on the GPU. And it has 50 values because we use the embedding of size 50. Glueon NLP has a number of utilities to help do all these comparisons. So it's got cosine similarity for one. And we can use this to compare these 2 word embeddings and see the similarity between them. So for BBC and television, if we run it through the similarity function, we can see they're 80% similar in this word embedding space. But if we compare BBC and Vegas, well, these 2 words are semantically not as similar. So they're similar at about 15%. So you can see we've got some semantic understanding in these embeddings. Now, I mentioned that these embeddings are useful as part of a neural network. This is because the embeddings learn so many different kinds of features, and you don't know which of those features out of the 50 or 100 embeddings are useful to your problem. And that's what you can use a neural network for if you have labeled data like we do in this case. And it's going to work out which of those features is more useful to your problem. So by taking your pseudo sentence, creating that embedding that we mentioned, we can apply a few even dense layers, which are fully connected layers, a very simple type of neural network, and we can stack a few of these layers using Glueon, and then make our prediction, which is binary classification, and train this neural network across all our samples, and it gives us a slight improvement. So we've got our PK down to 25.7. But again, there's still quite a few issues with our approach here. Let's look at some examples of what some potential problems could be. In example A, you'll notice that exactly the same words are used in both of these 2 sentences, but they've been rearranged and the meaning of the sentence is completely different. And by just averaging word embeddings across these 2 sentences, they're going to come up as the same, but the meaning of the sentence is completely different. So this is clearly wrong. Another example, example B, when we're trying to establish what a word means to be averaged in some kind of sentence embedding, well, that depends on context. So here, when we're trying to work out what the word Java means, well, that depends on the fact that we've seen traveling before. So it's more likely to mean the island than the programming language, for example. So we need to take that context from before into account before deciding on what the embedding should be for that word. And then in example C, this shows that the context could actually come from the future as you're reading sequentially. If I went to the bank, could be a riverbank or it could be a financial institution. So you get to the word money and then you know what the word bank means. So we need to include some of this context before creating the embeddings. So how do we do that? Well, there's been a really, really popular method for doing these contextualized word embeddings, and it's called BERT. And it's a model that was introduced in 2018, so it hasn't been around that long. But still, there's been a load of other models that have been created around it and improvements upon the basic BERT model. And so a few that you may or may not have seen before include Roberta, which was an improvement. It was BERT trained on a lot more data and also a few little tweaks here and there to improve the performance. Albert, which is a lightweight version of BERT, because BERT is quite a heavy model, memory intensive. And then the BERT model has been fine-tuned on different data sets as well to make the embeddings more relevant for those domains. So here's some examples such as clinical BERT, SciBERT, Camembert, BioBERT, and Patent BERT, all in different domains. With the Roberta embeddings specifically, so this is a modification of the BERT model. So we're again working with this embedding for each sentence and comparing every sentence to every other sentence. We can start to see even more patterns coming through. So this is starting to look more like that ideal situation. And here we've picked up on 3 of the segments using a slightly different method. And we've got a PK of 23.4. So every time we're bringing this number down. With Glueon NLP, let's see how we can get these BERT embeddings. So the first thing we need to do is establish or get the model from the model zoo. We can use the get model function for that, and we specify the particular model that we're interested in, the data set that we want to use that was used for pre-training the model. And then I mentioned there was these utilities that transform the data in exactly the right way for the specific model that you're using. Because we're using the BERT model, we can use the BERT tokenizer to break the sentence down into tokens in exactly the same way. So here, the sentence above has been broken down into different tokens. And now we have a BERT sentence transform, because BERT expects a certain input with actually 3 different inputs here. But you can just provide your tokens, apply the transform, and now one example of the inputs to BERT is something called the token IDs. So I mentioned that every token has to be converted to a number before it gets passed to the neural network. And we have this lookup to see what the associated index is for every word. And you'll notice 2 extra things here that have been added. So at the start of the sentence, we've got a number 2. And this is like a special token that BERT needs to indicate that the sentence is starting, and a 3 at the end that indicate that the sentence has finished. Now, all of these details change depending on which model you use, and it's really hard and it's really easy to forget some of these extra small little changes. But if you're using these preset transforms, then it's a good way to get started so you won't forget these. Now, with our outputs from the transform, we can pass that to the BERT model, which is just down here. And our output from the model, we have 2 things. So first of all, we have word embeddings. So for every word, we have a contextualized embedding. And then we also get a sentence embedding, which is a pooled version of all of those word embeddings. So we're going to use the sentence embedding in this case, because that's how we want to represent each sentence. So how did BERT get its representative power? And there was 2 tasks that were used for BERT pre-training. The first one, and probably the most important one, is called masked language model. You have a huge corpus of text in which to train BERT on, and you provide random sentences from this corpus. The first thing you do is mask out a proportion of these words. And then the objective of the BERT model is trying to guess what those words were that you've masked out. And to do well on this problem, this BERT model has to take into account the whole sentence, has to have a good understanding of that, and also to some extent some understanding of the world to be able to fill in the gaps. And if you train on a huge corpus of data, you're going to get some of that information distilled into the model. And then the second pre-training task to give BERT its power was the next sentence prediction challenge. So you take 2 consecutive sentences, and BERT has to work out whether the second sentence follows on from the first, or whether that second sentence was just randomly picked from the corpus. And so that needs some understanding of both of those sentences to be able to come to that conclusion. And so it's these 2 pre-training tasks that are useful in creating the embeddings. But that's just pre-training. Then when we're using the model ourselves, we're going to pass our sentence through and get the embeddings. We're not actually going to apply this problem. But pre-training is a really good step. And I mentioned there was all these different modifications and variants of BERT because they've been pre-trained on separate data sets. And you can actually update the BERT model and do some extra pre-training and fine-tuning on your own data set. So if you've got a lot of data, this is a really good way of making those embeddings even better for your particular domain. So how do you do that? Well, to begin with, you need some text. So we've got a corpus of text in a just regular text format. And then Glueon NLP provides a number of different training scripts so you can fine-tune all of these models. So for the BERT model, you can find these scripts at Glueon NLP/script/BERT. And we have a run pre-training script. And here all you need to do is specify where the text is that you want to run these 2 pre-training tasks on. And once you run this file, it's going to do those pre-training tasks on your own data. It's going to run the masked language modeling, the next sentence prediction. If you've got a lot of data, then this could be quite time-consuming. but the script supports and leverages all of that power that Apache MXNet provides. So you can run this across multiple GPUs, and you can also run this across multiple instances. And when you're running on multiple instances, it supports things like Horovod, which can be used for efficient training across multiple instances. And you just change your communication backend in those cases. Here we've got a pre-trained argument, and this is saying that we don't want to train from scratch. We want to start off from where BERT was when it was trained on a huge corpus and just continue from there to make our model even better, which can be really useful. This is really similar now to what we did with the word embeddings. I mentioned that the embeddings can have many, many features, some of which are not relevant to our problem. As an improvement to using the dense layer approach, we can use something called a bidirectional LSTM. So it's bidirectional in the sense that this layer works both forward and backwards. So you see those two arrows. And LSTM stands for long short-term memory. So in addition to taking some of that long-term context into account, which could include things like the topic shifts, we've got the short-term element that it can use input from the particular sentence that you're on. So this could be looking more at the words in that sentence to determine whether there's a topic break. So we've got our sentences at the bottom. We calculate the embeddings for every pseudo-sentence, and then we work both ways to determine the prediction for that given pseudo-sentence. And the prediction is, again, binary classification. Is there a change at this point or not? One problem we've got here is that we're using a BERT model, we're using LSTM layers. Our model is quite complicated, and it would be getting quite hard to train at this point. So we have to use some of the features included in MXNet and Glueon NLP to make training much, much more efficient. And an important concept is something called a bucketing strategy. So this is really important when we're working with sequences, which we are. We've got sequences of text and documents, but where the sequences are all different kind of lengths. So we have some short documents, we've got some long documents. And when you are training a neural network, you need to provide batches of data, because to use your GPU efficiently, you need many samples so the GPU can parallelize all these examples. And a very naive approach is to just take a random sample of your documents. If you do that, because all of your documents need to be converted to numbers and to be put into an array, you actually have to pad the short sentences to the same length as the long sentences. So in this case, we've got 5 or 6 samples per bucket, and we've padded all of the samples in that bucket to the length of the longest. And when we do padding, that is essentially wasted compute on the GPU. There's no learning that is going to come out of that padding, but we still have to process it and go through the whole neural network. So our aim really is to reduce the amount of padding where possible. For this case, as a baseline, our average padding was 11.7. So let's see if we can do any better than that to reduce the padding. A quick fix is to shuffle all of your samples and put all of the long documents in the same bucket and all the short documents in another bucket. And using this approach, we can reduce the padding to 1.7. So that's much, much improved. But even better is to change the batch size depending on the length of the sequences. And the idea here is to, every time you run through the network, you want to give a similar number of sentences through the network. If you didn't increase the batch size, you'd be doing less work for the short sentences. So for the short documents, you have more of those, and you pass it through the network. And this can improve training speed as well. With Glueon NLP, let's have a quick look at how you do this in practice. So let's say we've got 3 examples here, all of different lengths. These are documents. We've got a document 219, 338, and 477 in terms of how many sentences there are. And we can use a fixed bucket sampler, which is we specify the lengths of all our samples in the data set, and it's going to use this to work out which bucket every sample should go in. We want our batch size to be 16, so 16 documents to the network each time. and we want 10 buckets in total. Running this through, we can print out the statistics for our data set. So we have 10 buckets of different sizes, and you'll notice that the batch size actually is higher than 16 in those cases where the key or the length of the documents is smaller. So for 68, which is a short document, we have 58 of those samples. And this is all going to be done for us. And then just to note, the batchify function is going to be our method for combining different size sequences. So we have a short sequence and a long sequence. The batchify function controls how we can combine those two. And here we're just using a technique called padding. So it's going to add zeros to the short sentence to make it in total the same length as the long sequence. We provide these to the data loader, which is an MXNet construct used providing batches to your data, to your neural network. And here, if we run the training data loader, we can see that we have a batch of 24 samples. And all of these samples are of length 164 sentences. Let's visualize the training. So this is as the training is progressing. Along the bottom, we have the labels, which are the ground truth labels from the editors. Along the top, we have the probability from this particular model of there being a segment break at that given point. And then once the probability gets over a certain threshold, we can see that the model predicts pretty accurately where these segment breaks are going to occur. And the first thing it learns is to drop that probability down from 50-50 because there's a lot more samples of not segment breaks than segment breaks. With this model, we can see the same example, the probabilities spike where it should do. And even in the last example that's technically not over the threshold that I defined, we still have some signal. So this is really good for this example. And this was a test set example. This wasn't in the training data. And our PK comes a lot down to 13.4. And the last technique I'd like to talk to you about is something called metric learning. So I mentioned that there was all of these different features of the embeddings, some of which are relevant, some of which aren't. So with metric learning, the idea is to fold this embedding space in such a way that the sentences from the same segment appear close together, and sentences from different segments are pushed further away. And we do this through a technique called triplet loss, where you specify one sentence, you pick from random in the document. You pick another positive example sentence, which must come from the same segment. And then you pick a negative example, here in red, that has to come from a different segment. And if in the embedding space, you have the red example closer to the blue than the green, we need to change the network. So you update the network, and you push the red example further away, and you bring the green example closer. And you do this millions of times over as you warp your embedding space to give you a better representation, better embedding space to work with. Using this technique, we actually improve the PK in a generalized form. So the problem with the PK before was the model was overfitting to certain programs and certain documents. But with this approach, the PK remained the same for out-of-domain programs as well. So this was much improved in terms of generalizability of the model. And in the coming weeks, we're going to be announcing deep metric learning playground, which is going to have 12 state-of-the-art deep metric learning algorithms, all implemented with MXNet Glueon, which means you can bring your own data really easily and create these embedding spaces for your own data. And there are new state-of-the-art results included. And lastly, just on deployment. So with SageMaker, there's a few options that help for deploying these trained models. We have SageMaker Neo that you can use to deploy to different target devices. We can deploy to Intel devices, NVIDIA GPU devices, and it's going to optimize specifically for that hardware. Then for the BERT model that I've been talking about, we have different quantization options available. So you can reduce the model size by up to half, improve the speed of the model substantially, all of this for just a very tiny reduction in terms of loss of accuracy. And this helps you deploy a BERT model on different types of infrastructure that doesn't have the memory resources that you had on the GPU training device. And then there are some options from SageMaker to deploy to endpoints. You can use partial GPUs with elastic inference. You can deploy to edge with AWS IoT Greengrass. And if you want to apply batch transforms offline, you can use Amazon SageMaker Batch Transform. So just to wrap up, Glueon NLP is a really great starting point if you've got natural language processing problems. And Apache MXNet, the framework that's under the hood for Glueon NLP, is a really efficient and optimized framework, so you're going to get really good performance from it. And then SageMaker has a number of different tools available to help you while you're training these models. So you have automatic model tuner for the hyperparameter optimization, the debugger and experimentation tools that I mentioned before. And then lastly on BERT, it's really become the sort of new baseline model for natural language processing. So I would recommend and encourage you all to just try it out with Glueon NLP for your natural language processing tasks. And yeah, we've got lots of ideas for future work on this one. But thank you very much for joining today.